Welcome to 7th part of kinetic theory. In this part, you will learn about mean free path and Avogadro's number. Mean free path. Molecules in a gas have rather larger speeds of the order of speed of sound. Yet a gas leaking from a cylinder in a kitchen takes considerable time to diffuse to the other corners of the room. The top of a cloud of smoke holds together for hours. This happens because molecules in a gas have a finite, though small size. So they are bound to undergo collisions. And as a result of these, they cannot move straight unhindered. Their paths keep getting incessantly deflected. This figure shows the zigzag path of a gas molecule if a molecule covers free paths lambda 1, lambda 2, lambda 3 and so on after successive collisions. And then its mean free path will be given by sum of these, means lambda 1 plus lambda 2 plus lambda 3 and so on, divided by the total number of collisions. Or in simple words, you can say that the mean free path of a gas molecule is the average distance traveled by the molecule between two successive collisions. To find out the expression for mean free path, consider that the molecules of a gas are spheres of diameter d. Now focus on a single molecule with average speed v. It will suffer collision with any molecule that comes within a distance d between the centers. In time delta t, let it sweeps a volume pi d square v delta t, wherein any other molecule will collide with it as shown. In the diagram, the volume swept by a molecule in time delta t in which any molecule will collide with it. If small n denotes the number of molecules per unit volume, the molecule suffers n pi d square v delta t collisions in delta t time. Thus, the rate of collisions is n pi d square v, or the time between two successive collisions is on average is given by tau. It is pronounced as tau. And it will be equals to 1 divided by n pi v d square. So the average distance between two successive collisions, I have already told you we will call it as mean free path, let it be denoted by L, will be equals to v into tau. So it will be 1 by n pi d square. In this derivation, we have imagined that all other molecules are at rest. But actually, all molecules are moving and the collision rate is determined by the average relative velocity of the molecules. So we need to replace V by VR in equation 1. So the exact value experimentally it is found that L comes out to be 1 divided by under root 2 n d square. If m is the mass of each gas molecule, then the density of the gas will be rho equals to m into n. And by putting it in the formula of mean free path, you will get it m equals m divided by under root 2 pi d square rho. Here lambda bar is denoting the mean free path. You can denote it by L also. For 1 mole of a gas, PV is equals to RT, or P is equals to RT by V, and multiply and divide it by N, you will get N kBt, or the value of N will be P upon kBt, and therefore the mean free path will become kBt upon under root 2 pi d square P. Here are the factors on which the mean free path depends. It depends directly proportional to the mass of the gas molecule, inversely proportional to density of the gas, inversely proportional to square of the molecular diameter, directly proportional to absolute temperature of the gas, inversely proportional to pressure of the gas. Avogadro's number. It is the number of atoms present in 1 gram atom of an element or the number of molecules present in 1 gram molecule of the substance. In general, it is the number of particles present in 1 mole of the substance. Its most accepted value is 6.0225 into 10 raised to power 23 per mole. Its importance is in the calculation of actual weight of one atom of an element, and that will be the atomic weight divided by Avogadro number. To calculate the actual weight of one molecule of a substance, and that will be the molecular weight divided by Avogadro's number. To find out the number of atoms present in given amount of an element, it will be the Avogadro number divided by atomic weight into m gram. To find out the number of molecules present in given amount of a substance, it will be Avogadro number divided by molecular weight into m. And to find out the number of molecules present in given volume of a gas at S.T.P, the 22.4 liters of every gas contains Avogadro number of molecules. Therefore, the number of molecules present in V liters of gas at standard temperature pressure will be the Avogadro's number divided by 22.4 into V.